Well, we thought we would look at some practice problems with the second fundamental theorem of calculus. In these problems, we're going to be looking for the derivative of each of these functions. So we're really going to be playing off that second fundamental theorem. And I want you to remember the criteria for the second fundamental theorem. It says that if there is a function, some function in the upper bound, a number, a constant in the lower bound, then when you take the derivative of a function that's defined as an integral, you can simply make this substitution for the variable as long as you make sure to multiply by the derivative of the bound. Let's kind of walk through that. If we're looking for g prime of x here, I notice that the upper bound is where my function is located. I notice the lower bound is a constant, so I'm going to substitute 3x in for t. But I'm going to make sure that then I multiply by the derivative of the bound. So the derivative of the bound here is 3. And then we just need to clean it up a little bit. That gives me 6x plus 3, and then we're going to distribute a 3 to that. That will give me 18x plus 9. We're going to use a similar approach for these. We're just going to have to be really careful about making sure our criteria are in place and then that we multiply by the derivative of the bound. Okay, so constant in the bottom, function in the upper bound. When we take the derivative, we can substitute x to the fourth in place of t. And then we've got to multiply by the derivative of x to the fourth, which would be 4x cubed. Okay, and then we simplify. So 3 times 4x cubed will give me 12x cubed. And then the square root of x to the fourth would be x to the second. So I end up with 12x to the fifth. Okay, look at number 3 then. Notice that the bounds are backwards. So I need the 2x in the upper bound and I need the -1 in the bottom. To do that, to switch your bounds, remember your property of definite integrals, you can do that if you put a negative in front. Now we have everything in place for the fundamental theorem and we can take the derivative. So we'll substitute the 2x in place of the t here and here. And then we'll be sure, oops, I'm missing a parentheses, and then we'll be sure to multiply by the derivative of the bound, which is 2. So let's go ahead and multiply now. I've got negative, I'm going to bring this 2 in front. And then 2x squared would be 4x squared. And then 2 times 2x would be 4x. And then I'm missing primes on those, forgive me. Then we'll distribute the -2. So negative 8x squared minus 8x. Okay, now our next one uses a trig function. So, but my rules are still the same. So my constants in the lower bound, my functions in the upper bound, I'm going to take the derivative by making the substitution and then making sure to multiply by the derivative of the bound. So the derivative of cosine is negative sine x. So I've got -2 cosine squared sine. All right, number 5 here, we have the lower bound as the constant, the upper bound is the function. So we take the derivative by substituting in that upper bound and then making sure we multiply by the derivative of that upper bound. So the derivative here would be 2x plus 2. Now, just some cleanup. Let's see, I'm going to distribute the 3. That'll give me 3x squared plus 6x minus 2, and then 2x plus 2. We could FOIL this out if we wanted, not FOIL, we distribute, right, into long polynomial. Don't really have to, but you could if you wanted to. All right, number 6 then, again, we have this bound problem, right? We need the function to be in the upper bound. We need the constant to be in the lower bound. So let's switch those first. and then we'll take the derivative. So oops, and I forgot a minus in front. Got to have that minus in front when we switch those bounds. So I'm going to substitute. I'm going to get e to the ln of x plus ln of x, and then times the derivative of ln of x, which is 1 over x. Now, e to the ln of x, we know e and ln cancel. So right there, I'm left with x. And then let's distribute the minus and the 1 over x at the same time. That will give me -1 minus ln of x over x. So a little bit of algebra there at the end. So this fundamental theorem actually shows up in some of the free response questions, particularly ones where the function is given by a graph. So let's look at a few of these. We're told that the graph of little f of t here is shown to the right, and capital F of t is given by this integral. And we want to answer these questions. So I'm just going to highlight that integral. Okay, so we want to find the value of capital F of 0. So we're going to substitute in a 0 for x. And so that would make that upper bound 0. And so this is really saying, okay, go find the area from -6 to 0. So that is this semicircle here that's below the x-axis, and it's this triangle that is above the x-axis. So we're going to have to account for their location as well. So let's do the semicircle first because it's negative of 1/2 pi. Now its radius looks to be 2. So I've got 2 squared. And then we've got the triangle here, 1/2 times the base is 2 times the height is 2. And so f of 0 ends up being, let's see, 2 squared is 4 times the -1/2 gives me -2 pi plus 2. Now let's do the same for capital F of -1/2. So we're going to substitute -1/2 in for x. So that looks like we're doing the area from -6 to -1. Right? Think about that 2 times -1/2. And so I'm going to erase my shadings here so we can look at them a little bit closer. So we're going from -6 to -1. So that's the semicircle, and it's this tiny square right there above the x-axis. So we've already done the area of the semicircle back in number 7. So I'm just going to use that value, like work smarter, not harder, right? Look like the semicircle gave me an area of -2 pi. And now instead of adding this triangle, I'm going to add just the tiny triangle, which has a base of 1 and a height of 1. So I get that f of -1, capital F of -1/2 is -2 pi plus 1/2. Now let's then switch to look at the derivative. So we want the derivative of capital F. Let's find that. So the lower bound is a constant, the upper bound's a function. We're good there for second fundamental theorem. So capital F of x, we're going to substitute the bound, would be f of 2x times 2, because we got to take the derivative of the upper bound. Okay, so if I want capital F prime of -2, that would be f of 2 times -2, which is -4, times 2. So f of -4 means to go on this graph. When x is -4, what is the y value? That would be -2 there. So capital F prime of -2 actually is -4. Okay, let's look at capital F prime of 2.5. So we plug in 2.5 here. 2 times 2.5 is 5. So we've got f of 5 times 2. F of 5 means to go on this graph. Find the y value when x is 5, which is 2. So capital F prime of 2.5 is 2 times 2, which equals 4. Finally, the second derivative. Okay, so the second derivative of capital F prime, second derivative of capital F, we're going to take the derivative of this function. So we're going to have f prime of 2x times 2 times 2. Now think about where the 2's come from. The 2 comes from here. The second 2 comes from the derivative of the inside functions. We had to do a chain rule there. So we know that capital F double prime of x is 4 little f prime of 2x. And now we want to find that at 0. So capital F double prime of 0 is 4 times f prime of 0. Now f prime of 0 means to go on this graph and find the slope. So we need the slope when x is 0. And it looks like it's this line segment rising 3 and running 3. So that's a slope of 1. So we get 4 times 1, which is 4. Okay, now let's just switch graphs a little bit. We're going to use the same idea. We're being told that capital G of x is given by the integral from -2 to x of little f of t. So in number 12 here, we're trying to find capital G of 3. So we would plug in 3 for x. So we're doing the area from -2 to 3. Okay, so let's look at what that area looks like. From -2 to 3. Okay, so I see these two triangles are canceling each other out. I hope you can see that as well. So then I've got this area from 1 to 3 I've got to think about. Okay, so I'm going to probably do this little area here between 0 and 1. I'm going to do that as a trapezoid. And then the area from 2 to 3, I'm going to have to do the rectangle and subtract out the quarter circle. Let me show you how I would do that. So remember, from this triangle and this triangle, I'm letting them cancel each other out. I'm not even going to worry about their area. So now I'm going to do the trapezoid from 0 to 1. Okay, so that is 1/2 times the height, which is 1, and then I'm going to add the bases. The bases are 2 and 4. Now remember, this is below the x-axis, so I've got a negative on it. And there I've added my bases. Okay, now let's do the rectangle. And I'm erasing so you can see my rectangle. I want the rectangle here. And then I'm going to subtract out the quarter circle. But they're negative. Okay, so it's a little interesting. I'm actually going to subtract the rectangle and I'm going to add back the quarter circle just because they're below the x-axis. So the rectangle is 2 by 4. Okay, so 2 by 4. It's negative because it's below the x-axis. Now I don't want to account for the quarter circle, so I'm going to add it back. So the quarter circle would be 1/4 pi times my radius is 2 squared. All right, let's figure out our value. So 2 plus 4 is 6 times -1/2 is -3. Then I got my rectangle was -8. Then I'm adding my quarter circle back, which is pi. So I got a -11 minus pi for capital G of 3. Okay, let's find capital G of -4. So I'm going to put that in my bound for x. And I want you to see that our bounds are backwards. Because our bounds are backwards, we've got to use a negative and flip those bounds. Okay. So let's look at what this area is. This area And I have to erase because these shadings get in my way. This area is from -4 to -2. So that's all of this. I don't know about you. That looks like a rectangle and a triangle sitting on top of it to me. So that's how I'm going to calculate it. Don't forget you have the negative in front. Okay, so I'm going to do the rectangle. That's a 2 by 2. And then I'm going to do the triangle sitting on top. So that's 1/2. The base is 2. The height is 2. So let's see. I've got 4 plus 2. That'd be 6, and put a negative on it. So there's my g of -4. Now, let's take the derivative. Okay, the derivative of my integral function capital G would be f of x. Lower bound is a constant, upper bound is a function. Make our substitution. Okay, so if I want g prime of -2, then that really is little f of -2. Remember, this means to go on the graph and find the y value at -2. That would be 2. And then for 15, we want g double prime. So if g prime is little f, then g double prime is f prime. So g double prime of -5 would be f of -5, f prime of -5. That means to go find the slope at -5. The slope at -5 here looks to be up to over 1. So g double prime of -5 would be 2 over 1, or 2. Okay, just a few more. And these are just a little bit more complicated functions. So we want to make sure we understand what's going on, right? So look at how g of x is defined. It's the integral from 0 to x of t to the third e to the t. So problem 16 wants us to find g prime. So let's find the equation for g prime first using our second fundamental theorem. The constant is in the lower bound, the function's in the upper bound. So I get x to the third e to the x, and then I want that at 1. So I get 1 cubed e to the 1, which is just e. Now 17 wants the second derivative. So we need to take the derivative of this. I want you to think product rule. So first times derivative of the second plus the second times the derivative of the first. And now you're plugging in 1. So 1 cubed is 1. Then I get e to the 1 plus e to the 1 times 3. So I've got 1 e to the 1 plus 3 e to the 1s. That gives me 4 e to the 1s, or 4e. All right, look at the last two we have here. Let's see, h of x is defined. Notice your functions in the lower bound, your constants in the upper bound. We're going to have to change that if we want to use the fundamental theorem. So we switch them by putting a negative in front. And now we can find the derivative. Okay, so that's h prime equals, put in the x squared. So you've got x squared to the fourth. Then we multiply by the derivative of x squared, which is 2x. Gives me -2x square root of 1 plus x to the second, x to the fourth would give me x to the eighth here. And now 19 wants us then to use that and find it at 1. So h prime of 1 would be -2 times 1 times the square root of 1 plus 1 to the eighth, or -2 times the square root of 2. So I hope that helps. It gives you a little bit of variety of the types of questions you can see over the second fundamental theorem, those where you're just asked to find the derivative, and also those where you're asked to apply it to looking at a graph. So really make those connections. And if you have any questions or comments, please feel free to leave them below. I am happy to help in any way that I can. Bye for now.